Welcome to our talk on array updates. This is joint work with Michael Cohen from Stanford, Tang from Peking University, and Yanjing Wang also from Peking University. So I will first give you the background of this work, and we'll see a simple assignment operator from dynamic logic will play the magic to connect the didictal and array knowledge and updates. We want to repeat the successful story of dynamic epistemic logic, not only for the dictal knowledge and updates, but also for the array knowledge and updates. Standard epistemic logic mainly focuses on the didictal knowledge expressed by knowing that phi, knowing a proposition phi is true. But actually, knowledge is expressed by various other expressions such as knowing what, knowing how, knowing why, and so on. For example, knowing how to prove a theorem requires to have actually a fixed proof which can work to prove the theorem. And this kind of knowledge are usually called array knowledge, or say knowledge of things. Most of them share the general logic form of there exists x, knowing that find x. In other words, there exists something you know of that thing phi holds. So the dynamics of didictal knowledge, or say the knowledge expressed by knowing that, is well studied, especially in dynamic epistemic logic. But how can we handle the dynamics of the array knowledge? This is the topic of this talk. Of course, didictal updates may sometimes also change the array knowledge as well, but we care more about generating the array updates. As an example, consider the knowledge and updates about the value of a. So in didictal knowledge, you can say, you know that a equals to 8. The corresponding simplest dynamics is to publicly announcing that a equals to a. And the corresponding array knowledge is knowing what a is. And the array updates is publicly announcing what a is. You may think maybe we can use the didictal updates and didictal knowledge to mimic the array updates and knowledge. For example, announcing what a is roughly amounts to announcing a equals to 0.1 if a is actually equals to 0.1, and announce that a equals to pi if a is actually pi, and so on. So you need a infinite combination of those announcing that operators together. But if a has uncountably infinitely many values, do we need to introduce all these uncountably constant symbols into the language to handle this kind of thing? Do we need to combine all these infinitely many announcements together? We should be able to do without those infinite stuffs. Actually, you can introduce a new operator to handle such the array updates. For example, we introduce the public inspection operator in the literature, and we can handle the axiomatization, but with some limitation of the language. For example, without the didictal know that operator. Alexandru Bartek also introduced various new relativized epistemic operator, which can pre-encode both the announcement, the didictal announcement, and the array announcement. But the general trouble is when you introduce such new operator, then you will have some technical troubles which are not in the standard dynamic epistemic logic. For example, the numerical axiom, which is very central in the dynamic epistemic logic, doesn't work anymore here because the array updates are local in the sense that it depends on the actual word to see what exactly the effect of this update is. For example, announcing the value of A depends on the actual value of A on the current word. However, in the standard dynamic epistemic logic, the, say, announcement and other operators are somehow global in nature. So this is actually the reason behind the failure of numerical axioms and many other things for the array updates. So without introducing new operators, like particular new operators for the array updates and other heavy machinery, can we do better by introducing something much lighter? And more importantly, can we capture the more complicated array updates? For example, you may want to capture the event telling agent A the values of A and B, but at the same time, let agent 2 be ignorant about which is which. So this is also some kind of array updates, but it's not a public event. Do we need to introduce all kinds of new array operators for these kind of updates? Can we do better in a simpler way? The answer is yes. And this is the point of the paper. Actually, we can almost repeat the success of dynamic epistemic logic by adding just one little innocent operator to handle all kinds of array updates and array knowledge. So let's see how can we use a simple operator to bridge actually the world of the dictal and the world of the array. So the operator plays the magic is the assignment operator from dynamic logic. If you have ever taken a programming course, you will write the simplest program, such as assign some value to some variable. And actually, this is the point of this assignment operator. So you just assign the current value of t to the variable x. Already in the early days of dynamic logic, people observed that this assignment operator can function as the so-called lambda abstraction, which is actually turning a formula with some variables into some predicates. And these operators are used to distinguish the array and the dictal readings in first-order modal logics. For example, there are two readings of the sentence. The number of planets in the solar system is necessarily greater than 7. So the dictal reading is the number of planets as a non-rigid designator, whatever the real number is necessarily greater than 7, which is obviously false. This is not a necessarily true proposition. But in terms of the so-called array reading, the number of planets is referring to a number, which is 8. So if you just say the number 8 is necessarily than 7, then it is obviously true. So different readings will affect the truth value of the sentence, and it's better to distinguish different readings in our logical language. I won't go into the details, but actually the assignment operator can be used as the lambda abstraction to make the distinction. So the idea is you first fix the value of x as the current value on the real world of C, and then you just say it's necessary that this value is greater than 7. So in this way, you can capture the array reading of this sentence. And this assignment operator also was used in Bartol-Couey's work to distinguish the array detector rating, and also in our previous work of handling term epistemic logic without the assumption that all the names of agents are common knowledge. In this work, we don't need to handle the term modalities, and we will simplify the whole picture and add the dynamics. So let's go into the details. So in our basic static language, we have the terms and we have formulas. Terms can be a variable, can be just a non-rigid designator A. And in the formulas, we can write atomic formulas just like in the first order logic. And we have the usual Boolean connectives, we have the K operator, and we add the assignment operator. It says if you assign the current value of t to x, then phi holds. So the model is in first order model logic. You have the non-empty set of possible words, you have a constant domain, you have the epistemic relation, you have interpretations for predicates, you have the interpretation for the non-rigid designators, or say the names. It's important that the interpretation for predicates and for names are non-rigid, and they depend on the word. And a pointed model is a triple, where you also need the assignment for variables sigma. So assignment sigma for each assigns each variable a object in the domain. And you can lift this assignment to also the non-rigid names in your language. The semantics is mostly as what you expected, except the assignment operator is just to change this sigma to a different sigma, where the assignments for other variables are the same, but the assignment for x is changed to the actual value of t on the world w. So it depends on the current world. In this way, we can handle the knowing value operator we talked before by having this formula. You first fix, or say give the current value of a to x, and then you say you know that x equals to a. In this way, you can capture that the agent knows the actual value of a on all these indistinguishable words. And here is an example. You have two possible worlds, where here A is assigned to O1, and here is A is assigned to O2, and B is the other way around. And on this world, O1 has the property P. On this world, O2 has the property P. You can check that over this model, the agent has the dictal knowledge PA, but it doesn't have the array knowledge PA. Or say it doesn't know which object has the property P, although it it knows that A has the property P, but he doesn't know what A is. Okay, so we can axiomatize this logic by these axioms, which are also used in our previous work, taking the assignment operator as a modality, and we can prove the completeness for the logic over arbitrary model or over S5 model. But over S5 model, we will have the undecidability, unfortunately, because we can encode fittings quantifier free intentional logic. But for the logic over arbitrary model or over reflexive model, we have the decidability. Okay, in the last few minutes, I will just tell you the how to add the dynamics, because it's very straightforward. So the idea to add the announcement operator is just to add this announcement operator to the language and to have the usual semantics for this operator. You just change the model to the submodel where psi holds, and you check whether phi holds for this formula. And in this way, we can express a lot of complicated formulas discussed in the literature. For example, you can say, after announcing phi, you will know the value of C. So agent I would know the value of C given phi. And you will be able to say, how the value of D depends on the value of C, in the sense that you know that given you the value of C, you will know the value of D. And you can, express all kinds of other complicated Dirac and Didictal interaction formulas. And the important thing is you can still axiomatize this extension language, the extension of the language, by having another, say, reduction axioms, taking care how you can switch the announcement and the assignment operator in this way. So this is kind of trick we played. So you can check our paper for details. In this way, you can prove that adding this public announcement operator in the language, you don't say extend the strengthen the expressive power. And actually, you can add the event model, just like in the dynamic epistemic logic, by introducing the event models and the product updates. So by having the event models, you can handle the non-trivial Dirac updates we talked about. For example, you can use event model to handle agent A is told a password with agent 2 around, but agent 2 is not sure whose password it is. It could be Cindy's or David's. You can use this model to handle this. And the trick played is just to add the assignment operator in front of the event update operator. So you can verify that this combination of assignment and the event updates will give you the intuitive idea of the Dirac updates up there. So after this Dirac updates, agent 1 will know the value of C and D, but agent C doesn't have this kind of Dirac knowledge, but agent 2 doesn't have the Dirac knowledge, but agent 2 knows that agent 1 knows C, or agent 1 knows the value of D. You can even handle more complicated Dirac updates, like agent 1 and 2 are told two numbers, but agent 2 doesn't know which is which, and agent 1 knows which is which. And you can still have the, say, reduction axiom for this uh, event operator and the assignment operator. And we can use this kind of axioms to axiomatize the extended logic. And you can even add factual changes. Okay, so in conclusion, we can turn the array knowledge and updates into the corresponding we can turn the dictal knowledge and updates into corresponding array ones by the assignment operator. We can use a reduction axiom to capture the interaction of updates and assignment operator and have complete axiomatizations. The static logic is can also be axiomatized completely so as to dynamify the versions. And the assignment operator can strengthen the epistemic logic and to handle both the dictal and the array knowledge and updates. So for future work, actually, we can repeat what we did for dynamic epistemic logic. We can add, for example, the common knowledge operator, but we can also try to see how we can stay in the decidable world. And we can also extend the framework to capture more intuitive array updates and so on. So I hope the talk give you a very brief array updates on what our paper is about. So for details, especially about the array updates, the technical parts, please check our paper. And thank you for your attention.